Hello everyone and welcome to our next video on Doppler effect. In this video, first off, we're going to begin with having a look at a worked example with a moving observer now. Okay, in the previous example, we looked at a stationary observer and a moving source. Here we're going to look at a example with a moving observer. Now the question reads, what is the frequency heard by a person driving at 15 meters per second towards a factory whistle that is being blown at a frequency of 800 hertz? Assume that the speed of sound in air is 340 meters per second. Okay, now in this question, we can see that there's a moving observer and a stationary source. Okay, a factory cannot move. A factory is pretty much stationary. All right. So we have everything that we need for this question. Okay, that has been given to us so ever so kindly. Okay, so on our page, we can just write down here the frequency of the source is equal to 800 hertz. This was the factory. Okay, we have the VS. Okay, oh, let's get that out there. Oh wait, we can actually write that. VS is stationary, so it's 0 meters per second. We know that V is 340 meters per second, which is the speed of sound in air. And we also know that the velocity of the listener, VL, is equal to 15 meters per second. Now remember, in order to figure out here, they say it's driving towards a factory. So remember here in the signs, they said that the listener is moving towards the source. Therefore, VL is positive. All right, so VL is positive here in this question. Okay, it's driving toward a factory. All right, so therefore, this is a positive 15 meters per second. Okay, but the question has worked it out for us. Okay, so obviously step one, we analyze the question, which we have. Okay, now step two, okay, determine how to approach the problem, all right, based on what has been given. So we can use, yes, the Doppler effect equation, FL equals to brackets V plus minus VL divided by V plus minus VS times FS. Please notice here that before we eventually figure out our total question here, okay, what is important to note here, or a final simplified Doppler effect equation, the final form of it, we first need to write out the whole formula here first, right, before we can get to this formula here in step 3. First this, right, because there's a mark for this in the exam, okay, the full formula. All right, again, they've analyzed their problem where they've stated everything that they need. Okay, again, V is equal to 340 meters per second. VL is equal to 15 meters per second. VS is 0 meters per second. FS is 800 hertz. And FL, frequency of the listener, is unknown. That's what we're trying to obtain. The listener is moving towards the source, so VL is positive, as we've already discovered. And also, the source is stationary, so VS is 0 meters per second, which we also uncovered a little bit earlier. Now, step 3. Step 3, what we do is we calculate the frequency. Okay, we get our simplified Doppler effect formula. We know exactly what we're working with. FL is equal to V plus VL over V plus VS over FS. Oh, times FS, excuse me. Alright, so we sub in 340 plus 15, alright, divided by 340 plus 0 times 800. We get an answer of 835,29 hertz. Alright, and then we write down the final answer and we quote it that the driver hears a frequency of 835,29 hertz. And that, ladies and gentlemen, is our final answer. Okay, and there you go. That is full marks for this question. Right, so we've looked at two examples. We've looked at case 1 with a moving source and a stationary observer, and we've looked at a scenario with case 2 when we have a moving observer and a stationary frequency. Alright, I think we're ready to go and attempt a question on our own. Alright, so let's have a look here. Here for you. So what I'm going to do, I'm going to allow you to have a look at this question. Okay, I'll read the question for you. First of all, a train approaches a station at a constant speed of 20 meters per second with its whistle blowing at a frequency of 458 hertz. An observer standing on the platform hears a change in pitch as the train approaches him, passes him, and moves away from him. Alright? Now, question 1. Name the phenomenon that explains the change in pitch heard by the observer. Question 2. Calculate the frequency of the sound that the observer hears while the train is approaching him. Use the speed of sound as 340 meters per second. That's 4 marks. How will the observed frequency, in question 3, change as the train passes and moves away from the observer? All we have to do here is write down increases, decreases, or remains the same for 1 mark. And then question 4, how will the frequency observed by the train driver compare to that of the sound waves emitted by the whistle? Write down only greater than, equal to, or less than, and then give a reason for your final answer. Okay, so go ahead, attempt this question by yourself. Okay, and I'm counting on you to especially get question 2 correct. Alright, I'm counting on you to do that. Okay, and definitely question 1 as well. Alright, but I'm counting on you to definitely get question 1 and 2 correct. Okay, and question 3 and 4, don't worry if you do get a little stuck or you're unsure a little bit, come back to the video and then have a look at the solutions. Alright, go break some eggs. Right, okay, welcome back everybody. Hope you enjoyed that question. This was a nice question, I think. Let's go have a look at the solutions, shall we? Okay, so question 1. Question was, name the phenomenon that explains the change in pitch heard by the observer. Alright, and that's for 1 mark, and we definitely know that answer. It is the Doppler effect. Okay, definitely the Doppler effect. Alright, that was a straightforward, easy question. Okay. Question 2, though, was the one I was counting on you to get correct. And question 2 reads as follows. Calculate the frequency of the sound that the observer hears while the train is approaching him. Use the speed of sound in air as 340 meters per second. Okay, so what I've done here for you is you should have written this down on the right hand side of your page. Okay, the piece of information that I forgot, oh not forgot, but I did not put down was 340 meters per second as our V. That is our speed of sound in air. Okay, but that's already given in the question. Okay, so that's why I did not take it down. Okay, it's kind of counterintuitive. Okay, so as first things first, we write down our whole Doppler effect formula. Alright, V equals V plus minus VL. Alright, shift all over. V plus minus Vs. Alright, times Fs. Okay, now they told us that the train was approaching a stationary observer. He was standing on the platform and the train was approaching him, hence why Vs is negative 20 meters per second. The velocity or the speed of the listener is 0 meters per second as he's not moving. So therefore the formula how we're going to calculate FL is equal to V all over V minus Vs, right? We have our brackets, times Fs. Okay, and now this is equal to 340, right? All over 340 minus 20, right? Brackets, times 458. Right, times 458. Okay, that is all our information there. And if we plug this in onto our calculator, we get an answer of 486,633 hertz, okay, which is the frequency heard by the observer standing on the platform as the train approaches him. Okay, now let's have a look at question 3. How will the observed frequency change as the train passes and moves away from the observer? Write down only increases, decreases, or remains the same. Well, he hears the frequency or the sound of the train whistle the loudest when the train is approaching him or when the train is right by him. Now the train has passed him and is moving away from him. So it's clear to state and to understand here that the observed frequency, or the frequency heard by the stationary observer standing on the platform, will decrease. Hence the answer here for number 3, they told us only to write down increases, decreases, or remains the same is decreases. Alright, wonderful. Now let's have a look at question 4. Alright, question 4 here. Alright, question 4 how will the frequency observed by the train driver compare to that of the sound waves emitted by the whistles? Alright, let's read that question again just to wrap our heads around it. How will the frequency observed by the train driver compare to that of the sound waves emitted by the whistle? Write down only greater than, equal to, or less than, as well as let's give a reason for our answer. Well, this is how we can think about this question, alright? So the train driver is driving the train that is emitting the sound frequency of 458 hertz. Alright? Let me say that again. The train driver is driving the train that is emitting the frequency of sound at 458 hertz. So the velocity of the train driver is equal to that of the velocity of the train because he is moving with the train. Alright, so it's safe to say that the frequency that the train emits is the same frequency as what the train driver is going to hear it as. So the train driver is going to hear a frequency of sound equal to that of the train whistle. So therefore the answer is equal to, alright, we write down equal to, alright, and the reason we give, alright, the reason we give is the train driver has the same velocity as the whistle. Alright, because he's driving the train. So he's going at the same speed of the train. Alright, and that is 1, 2, 3, 4 questions answered. Just like that, easy peasy. Alright, hope you understand questions 3 and questions 4, especially question 4, okay? And I'll go through that question just one more time. Alright, the velocity of the train driver, or the frequency that the train driver hears, is equal to that of the frequency being emitted by the train whistle, because the train driver has the same velocity as the whistle.